You know, when we talk about a building's architecture, like a physical building, there's this built-in assumption of permanence. You dig a massive foundation, you pour thousands of pounds of concrete, you bolt the steel beams together.
Right, it's completely rigid.
Exactly. And eventually, the architect points at the skyline and just says, well, there it is. That's the structure. It will never change.
It's static by design. I mean,
Yeah.
you build it once, and barring some massive renovation, you simply have to live with the choices you made during the blueprint phase.
And there is something deeply comforting about that predictability. Like knowing exactly where the load-bearing walls are. You know, you can't just move a load-bearing wall on a Tuesday because you feel like it.
No, you definitely cannot.
But when you step into the world of modern cloud database architectures, that concrete suddenly starts behaving, well, like a liquid. We are looking at an architectural landscape today that is constantly shifting, scaling horizontally, tearing itself down, and adapting on the fly.
It's wildly dynamic.
Right. And to a traditional database administrator who is used to racking physical servers in a cold room, it can look incredibly chaotic.
It is the absolute definition of architectural muddy waters if you don't possess the foundational maps to navigate it. I mean, building an application in the cloud isn't just about renting a digital warehouse and dumping your tables in there anymore.
No, it's way more complex now.
It requires a surgeon's precision. It is about matching the exact, precisely right database engine to the specific speed, structure, and scale of the problem you're trying to solve in that exact microsecond.
And navigating that complexity is our mission for this deep dive. Today, we're taking you, the listener, through an incredibly dense, highly specific stack of technical slides.
Very dense.
Yeah. These materials aren't introductory. They are designed for IT professionals actively preparing for a major career milestone, which is the Google Cloud Professional Database Engineer certification journey.
The source material we are working with today is, frankly, unapologetically technical. It is built for people who live, breathe, and occasionally lose sleep over data consistency and network latency.
But you don't need to be a certified cloud architect to follow along with us. We are not going to sit here and drone on about API rate limits or just read bullet points from a slide deck.
That would be brutal.
It really would. Our goal is to extract the most fascinating insights, the architectural aha moments, to give you a shortcut to understanding how massive global applications actually function under the hood.
Think about the applications you use daily. When you refresh a social media feed, or when you load a massive multiplayer mobile game, or finalize checkout on a global e-commerce platform.
All that stuff happens instantly.
Exactly. But there is an invisible high-speed ballet of data occurring across thousands of miles of fiber optic cables. And understanding the choreography of that ballet is fundamentally empowering.
We have a massive journey ahead of us. We're going to start at the absolute bedrock, the infrastructure layer. We have to answer the question of whether we should manage our own database environments using Kubernetes or just hand over the keys to a managed service.
Right, the big debate.
From there, we are going to plunge into the wildly flexible, horizontally scaling NoSQL universe of Cloud Firestore. Then, because sometimes disk storage simply isn't fast enough, we're going to explore the terrifying but necessary world of in-memory caching with Cloud Memorystore.
Terrifying is a good word for it.
Yeah, we'll get into why it's so scary. And finally, because generating all this data creates an organizational nightmare, we will look at how enterprises govern their data using data catalog.
It is a really logical progression. We start with where the data lives, move to how it is structured, accelerate its delivery, and finally figure right out how to keep track of it all.
So let's get right into the infrastructure. The slides present this fascinating, almost philosophical dilemma right out of the gate regarding Google Kubernetes Engine, or GKE. The fundamental question is basically, how much control do you actually want over your database?
It's the classic cloud computing trade-off: control versus convenience.
The sources outline a very compelling case for running a database directly inside GKE. And looking at the slide titled Database on GKE, Why and How, they give us 4 major benefits that sound, honestly, too good to ignore.
They do make a strong pitch.
They really do. The first one is portability.
Portability is the holy grail for a lot of enterprise architects. By containerizing your database, wrapping it up in a neat Docker container and orchestrating it with Kubernetes, you effectively abstract away the underlying hardware.
So you aren't tied down to one specific vendor.
Exactly. You aren't tied to one specific cloud provider's proprietary virtual machine infrastructure. In theory, you can pick up that Kubernetes cluster and run it on Google Cloud run it on a competitor's cloud, or even drag it back to your own on-premises data center.
You are speaking the language of Kubernetes. It's like a universal adapter.
It is.
Now, the second benefit the slides highlight is minimizing latency and increasing consistency between the application layer and the database layer. I think about this kind of like a kitchen.
Okay, a kitchen.
Yeah, if your application microservices are the chefs and they are already running inside a Kubernetes cluster, it makes logical sense to put the database, which is the pantry, right there in the same room. You don't want the chef sprinting out to a separate building in the garage every time they need an onion.
That physical proximity matters immensely. The physical distance data travels over a network introduces latency.
Even over fast networks.
Oh, absolutely. Even if it's just a few milliseconds. If your application makes thousands of database calls per second, those milliseconds compound into a terrible user experience. Keeping the application pods and the database pods within the exact same cluster network minimizes that friction.
Makes sense. The third point they emphasize is better resource utilization,
Which Kubernetes is famous for. It plays Tetris with your workloads, it packs containers tightly onto the underlying server nodes, so you aren't paying for a massive server that just sits idle 90% of the time.
And the final point from the source is leveraging Kubernetes native infrastructure automation.
Right. If your engineering team has spent 2 years mastering Kubernetes tools for deployments, auto-scaling, and health checks for the web application, they can apply that exact same operational muscle memory to managing the database.
So they don't have to learn a completely separate, siloed management system.
Exactly.
Okay, so looking at that list, portability, ultra-low latency, perfect resource packing, and unified automation, it sounds like a no-brainer. It sounds like everyone should immediately move all their databases onto GKE today.
It does. Until you turn the page.
Yes, because the very next slide introduces a decision tree, and this is where the narrative just sharply turns. This entire flowchart is essentially a gauntlet designed to talk you out of doing exactly what the previous slide just pitched.
The tension here is brilliant. It separates what is technically possible from what is operationally sane.
Operationally sane, I like that.
The decision tree forces an architect to confront the reality of day-to-day operations.
The first hurdle on this tree is a simple question. It asks, does my database have Kubernetes-friendly features? If it doesn't, you shouldn't even attempt it. But if it does, it asks a follow-up. It says, is there an operator or project to help?
And we really need to pause here because this touches on a fundamental conflict.
Right. Because Kubernetes was originally designed for stateless applications, like an app that can just be killed, deleted, and restarted on another server without losing anything.
A simple web server, for instance.
Yeah. But a database is, by definition, stateful. It holds your company's most precious data. That data has to persist.
You've hit on the core friction. Managing state in a highly dynamic, ephemeral environment like Kubernetes is inherently dangerous. If a node fails, Kubernetes wants to instantly spin up a replacement pod somewhere else. But you can't just spin up a new, empty database pod. It has to have the data.
It can't just start from zero.
Exactly. And that is where the operator pattern comes in. An operator is essentially a piece of software running in your cluster that encapsulates human operational knowledge.
Like a virtual database admin.
Basically, yes. It knows how to safely back up a specific database, how to handle failovers, and how to safely scale it without corrupting the data.
So the flowchart says if you don't have a robust operator project to babysit this database, you then have to ask yourself, how much ops workload is acceptable? And it gives you a fork in the road. You can choose, I'll manage it, or not much.
This is the critical pivot of the entire cloud philosophy.
It really is.
Yeah.
Because if you look at the not much path, it routes you immediately away from Kubernetes and points to a box that says, use a fully managed DB. In fact, there is a massive blue text box on the slide labeled exam tip that explicitly states using managed service, e.g. Cloud SQL, is preferred.
This cannot be overstated. It is the golden rule.
I think about it like this. Running a highly complex stateful database on Kubernetes is like building a custom high-performance sports car from scratch in your garage.
Okay, I see where you're going.
You handpick every gasket, you tune the fuel injection, you have absolute granular control over every millimeter of the machine. It is an engineer's ultimate fantasy.
Oh, engineers love it.
But is that level of control worth the operational nightmare compared to simply leasing a reliable, fully featured luxury sedan from a dealership that handles all the oil changes and maintenance for you?
That analogy perfectly captures the dilemma. Building the custom sports car is intellectually satisfying. You feel like a genius when it works. But the reality of enterprise IT is the 3 a.m. pager alert.
Oh, the dreaded pager alert.
When that custom Kubernetes database implementation breaks down on a holiday weekend, you are the one who has to get out in the rain, open the hood, and figure out why the data isn't synchronizing.
It's all on your shoulders.
Conversely, when you use a fully managed service like Cloud SQL for a PostgreSQL or MySQL workload, Google acts as your mechanic. They handle the automated backups. They apply the security patches behind the scenes. They manage the high availability failovers. They handle the storage scaling.
So why would anyone ever take the other path? Like, why does the flowchart even offer a route that ends at run it on Kubernetes?
Well, you only arrive at that destination if you answer yes to every grueling prerequisite. Yes, it has Kubernetes features. Yes, there is an operator. And critically, when asked about the operational workload, you stubbornly declare, I'll manage it.
You really have to want it.
You only do this if you have a highly specific edge case. Perhaps you have stringent, non-negotiable compliance requirements that forbid data living in a managed service environment. Or perhaps you are running a massive, globally distributed, highly customized architecture, and you have a dedicated team of 20 elite site reliability engineers whose only job is to maintain that custom database.
So you essentially have to actively choose the operational burden because your business requires a level of customization that a managed service simply cannot provide.
The overarching lesson for these future database engineers is to swallow their engineering pride. Just because you possess the technical capability to build a wildly complex, bespoke infrastructure doesn't mean you should. Complexity is a massive organizational cost.
For you listening, this is a principle that extends far beyond databases. Every piece of custom infrastructure you build is a piece of infrastructure you are now legally and functionally obligated to maintain forever.
It drains your human capital.
Exactly. Defaulting to managed services frees up your smartest engineers to work on the application itself, the thing that actually generates revenue for the business, rather than just toiling away keeping the database lights on in the server room.
We are seeing a massive industry shift from focusing on the how of infrastructure plumbing to the what of business value delivery.
It's a profound shift. So establishing that the golden rule is use managed services whenever humanly possible, let's explore one of the most powerful managed services Google offers. We are moving away from the rigid tables of relational databases and entering the highly flexible world of NoSQL with Cloud Firestore.
This requires a mental pivot. We are leaving behind the strict guarantees and fixed schemas of traditional SQL and embracing dynamic data structures.
Before we dig into the architecture, though, we have to clear up a branding issue that the slides explicitly warn about. Slide 8 calls this out as an exam tip because it trips up almost everyone new to the ecosystem. I call it the name game.
Oh, the name game. It is notorious.
We have Firestore, we have Firebase, and we have FileStore. They sound identical. If you are rushing through a certification exam or just reading a technical white paper, it is incredibly easy to conflate them. So let's untangle this web permanently.
Let's start with the core technology we're focusing on, which is Firestore. Cloud Firestore is the actual database engine. It is a fully managed, serverless, NoSQL document database. It is the repository where the data is stored, synced, and queried at a global scale.
Okay, so Firestore equals the NoSQL database engine itself, the vault. What is Firebase?
Firebase is not a database.
Wait, it's not?
No. Firebase is an entire comprehensive development platform for mobile and web applications. It is a massive toolbox. Inside that toolbox, you have authentication services to manage user logins, you have crash reporting tools, you have performance monitoring, and you have cloud messaging for push notifications.
So Firebase is the overarching suite of tools for an app developer.
Precisely. And one of the most critical tools inside that Firebase toolbox happens to be the Firestore database. Mobile developers using the Firebase platform will utilize the Firestore database to store their app's user profiles or chat logs. Firestore is the database. Firebase is the ecosystem that surrounds it.
That distinction is crucial. Okay, what about the outlier, FileStore?
FileStore operates in a completely different universe. It is a fully managed, cloud-based, network-attached storage system, a NAS.
Okay.
Think of it as a gigantic, incredibly fast, shared hard drive floating in the cloud. It is specifically designed for unstructured raw files, not database records.
Unstructured meaning it has no concept of queries or documents or columns. It's just a place to dump files.
Yes. The slides outline the ideal use cases for FileStore, and they highlight workloads like media rendering, where massive video files need to be accessed by multiple compute nodes simultaneously, or life sciences and genomics processing, where you're dealing with terabytes of raw DNA sequence files.
Wow.
It is also used heavily in legacy application migrations, where an older piece of software hard-codes its storage to a traditional file system mount and just doesn't know how to speak to a modern object storage API.
So summarizing the name game, Firestore is the NoSQL database. Firebase is the mobile app development platform. Filestore is the giant shared hard drive for raw, unstructured data.
Once you map those out, the architectural choices become much clearer.
Let's zoom in on the data model of Firestore. Slide 10 provides a translation table. Anyone who learned computer science in the last 30 years likely learned relational databases first. You learn about tables, rows, and columns.
Standard SQL.
Right. But NoSQL requires rewiring that mental model. So instead of a rigid table that holds our data, the slides tell us Firestore uses a kind.
A kind is simply a category of objects. It serves a similar organizational purpose to a table.
And inside a traditional table, we have rows of data. In Firestore, a single object of data is called an entity.
An entity is the individual unit.
Inside a traditional row, we have columns like first name or account balance. In Firestore, these individual data rooms are called properties.
And this is where the divergence from relational databases becomes massive.
How so?
Well, in a relational database, every row in a table must conform to the columns defined in the schema. If you add a shoe size column to a user table, every single user row now has a shoe size slot, even if it's empty.
Right, it's a fixed grid.
Exactly. But in Firestore, an entity within a kind can have a completely unique set of properties. The schema is dynamic. One entity might have 5 properties, and the next entity in the exact same kind might have 50 entirely different properties.
That flexibility is staggering. And finally, every row needs a unique ID, a primary key to look it up. In Firestore, that translates directly to a key.
The key is the unique identifier for the entity.
So we have this wildly flexible, dynamic data model. But the obvious question is, when do you actually use it? Why abandon the safety and predictability of a rigid SQL table? The slides point to use cases like product catalogs providing real-time inventory or highly customized user profiles for massive gaming platforms.
It comes down to developer velocity and scale. If you are building a modern mobile application, the features you need today might be completely different from the features you need in 6 months.
Things change fast.
They do. A dynamic schema allows developers to push new features and store new types of user preferences on the fly without having to halt the database, run a massive schema migration, and pray nothing breaks. It allows the data model to evolve organically alongside the application code.
The source material is also very deliberate about defining non-ideal use cases. They explicitly tell you when Firestore is the wrong tool for the job. They say do not use it for an OLTP online transaction processing system that requires full SQL support.
If you are building a core banking ledger where money is transferring between accounts, you need the absolute ironclad guarantees of ACD transactions and the rigid constraints of a relational schema.
So you wouldn't use Firestore for my checking account?
Definitely not. You use Cloud SQL or Cloud Spanner for that.
Yeah.
NoSQL's flexibility becomes a liability when absolute cross-table transactional integrity is the primary requirement.
The slide also warns against using it for OLTP online analytical processing. If you want to do interactive querying for massive analytics, it says to use BigQuery. Why does a NoSQL database fail at analytics?
Because of how the data is stored physically on the disk. Document databases are great at retrieving an entire document quickly. But if a data scientist wants to calculate the average account balance across 1 billion user documents, a NoSQL database has to pull up every single document just to read that one property.
Oh, that sounds terribly slow.
It is wildly inefficient. BigQuery, on the other hand, uses columnar storage, meaning it stores all the account balances together on the disk, completely separate from the names and addresses. It can scan billions of numbers in seconds without reading the rest of the data.
You cannot use a screwdriver to hammer a nail. But here is a complication the slides introduce on slides 12 and 13. Firestore isn't just one thing, it actually operates in 2 entirely different modes, native mode and data store mode.
This is a foundational architectural decision that you have to make the moment you create the database instance.
Just looking at the naming conventions, native mode sounds like the modern intended path. It sounds like the evolution. If it's native, why would anyone ever choose data store mode?
It requires a bit of historical context. Google Cloud originally had a NoSQL database called Cloud Datastore. Separately, Firebase had a product called the Real-Time Database. Firestore native mode is essentially the spiritual successor that merges the best capabilities of both.
The superpower of native mode, according to the slides, is direct app-to-database development.
This is a paradigm shift. Traditionally, a mobile app doesn't talk to a database directly. The app talks to an API server, a middle tier, and that API server runs the security logic and talks to the database.
Right, there's always a middleman.
But native mode allows the client application, running on the user's phone, to establish a secure, direct connection to the database. It eliminates the need to build and maintain that middle-tier API layer for simple data retrieval.
It accelerates the development lifecycle incredibly. It also highlights real-time updates and offline mobile support.
If a document changes in the database, say a sports score updates, the database instantly pushes that change down to every single mobile app connected to it without the app having to refresh.
That's pretty cool.
And if the user's phone drops cellular service, the Firestore client library caches data locally, allows the user to continue interacting with the app, and automatically synchronizes the changes back to the cloud the moment the signal is restored.
That is massive for mobile UX. So native mode is clearly built for modern web and mobile apps. Why does Datastore mode still exist?
Datastore mode is highly optimized for legacy backend architectures and highly structured data at an immense scale. It retains the older entities in kind structure we discussed, but its key differentiator is its support for something called ancestor queries and strongly consistent results across complex hierarchical data structures.
So it's more for back-end systems.
Yes. It is typically used for server-to-database communication, where massive back-end compute engines are processing data, rather than direct-to-mobile client interactions.
And the warning on slide 12 is severe. It says in bold text, no compatibility between Firestore APIs used by native mode and Datastore APIs.
It is a one-way door. They use entirely different client libraries, different connection protocols, and different underlying query structures. You cannot build your application in native mode and then decide 6 months later to flip a toggle switch and switch to Datastore mode.
Wait, really? You can't just migrate it?
No, you would have to rewrite your application's entire data access layer.
That is the kind of mistake that gets an architect fired. Okay, let's transition to performance because slide 14 details an indexing rule that completely upends how traditional database developers think about queries.
Ah, the strict indexing requirement. This is the secret to Firestore scalability.
The slide explicitly states, Firestore ensures query performance by requiring an index for every query, every single query. If I come from the SQL world, I know that if I run a query on a column without an index, the database will complain. It might take 30 minutes to do a full table scan of a billion rows. The CPU will spike, but eventually it will grind through it and give me an answer.
Right.
The slides are saying Firestore will simply refuse to execute the query.
It will flat out reject it and throw an error back to the application.
That feels incredibly hostile to a developer trying to explore their data. Why is it so restrictive?
It is fiercely protective of its performance guarantees. Firestore makes a mathematical promise to its users. The performance of a query is proportional to the size of the result set, not the size of the data set.
Let's break that down.
If you write a query that asks for the top 5 highest scores, and your database has 100 records, it takes a few milliseconds. If your database grows to 100 billion records, and you run that exact same query for the top 5 scores, it takes the exact same number of milliseconds.
Wait, it doesn't slow down as the database grows?
It does not slow down.
That seems impossible.
The only way Google can physically guarantee that performance at a global scale is by strictly forbidding table scans. It forces you to pre-compute the lookup paths. Those paths are the indexes. By requiring an index for everything, the database engine never has to search. It only has to retrieve.
It refuses to allow a slow query because a slow, unindexed scan across a multi-petabyte database would consume so much compute power it could destabilize the entire regional cluster for other customers.
Yeah.
It is protecting the ecosystem.
Exactly. Now, the developer experience around this is actually quite elegant. The slides point out that for basic single-property queries, Firestore automatically generates built-in indexes behind the scenes.
But if I want to do a complex query like find all users in New York A&D who are over the age of 30, that requires a composite index across 2 properties.
And if you run that query during development without having built the composite index, the error message Firestore returns isn't just a generic failure code. It actually contains a direct hyperlink. You click that link, it authenticates you into the Google Cloud Console, and it automatically populates the exact index creation form you need. Just click Create.
Okay, that's actually a brilliant developer
He
experience.
really is.
But regarding how data actually gets into those indexes, there is a mind-bending quirk buried at the bottom of slide 14. It relates back to the dynamic schema of NoSQL.
The distinction between a missing property and an NUL value. This trips up so many seasoned SQL veterans.
The text says, if an entity is missing any of the index properties, it won't be included in the index and will never be returned as a result. If the property has an NUL value, it's included.
Yeah.
Compared to a human brain, missing and NUL effectively mean the same thing. There is no data there. Why does the database engine treat them as fundamentally different states of reality?
It is a profound concept in document database theory. In a relational SQL database, the structure is paramount. If you have a middle name column, that column physically exists for every row.
Yeah.
If a person doesn't have a middle name, the database explicitly inserts an NUL marker into that slot to indicate the absence of data within an existing structure.
The slot is there, it's just empty.
Right. But in Firestore, a document might literally not possess the structural concept of that property.
I think I need an analogy for this.
Let's imagine a database storing medical records for an animal hospital. We have documents for dogs, documents for cats, and documents for turtles. We want to build an index on a property called bark volume.
Okay, bark volume.
We go to the dog document and it says bark volume, loud. That goes into the index. We go to the cat document. A cat obviously doesn't bark. But perhaps the developer wanted to be thorough, so they explicitly created the property and set it to bark volume. NUL.
Acknowledging that the property exists in the app's logic but has no value for a cat.
Exactly. Because it was explicitly set to NUL, the cat document is added to the bark volume index under the NUL category. But then we get to the turtle document. The developer didn't even bother adding the property. The turtle document simply does not contain the text bark volume anywhere in its JSON structure. The property is truly missing.
So what does the indexing engine do?
When the engine scans the turtle document to build the bark volume index, it sees nothing, so it skips it entirely. The turtle document never enters the index.
Why is that a good thing?
Because it keeps the indexes incredibly lean and fast. If you have 1 billion documents and only 10,000 of them are dogs, your bark volume index only contains 10,000 entries, plus any explicitly NLL entries. Doesn't have to carry the dead weight of millions of irrelevant records. However, the gotcha is that if an application queries the database asking for all animals where bark volume is NLL, it will return the cat, but it will absolutely not return the turtle.
Because the turtle isn't in the index, and remember the golden rule, if it's not in the index, Firestore refuses to return it. That is a brilliant, subtle architectural detail that could cause a massive bug if a developer doesn't understand the nuance of NoSQL schemas.
It happens all the time.
Let's shift from indexing performance to physical reliability. Slides 16 and 17 cover the physical deployment locations, regions, and multi-regions, and the service level agreements, the SLAs, are staggering.
They define what enterprise-grade availability actually means in the modern cloud.
If you choose a regional setup, Google replicates your database across 3 distinct availability zones within a single geographic region. So maybe 3 different data centers scattered across South Carolina. This gives you an SLA of 99.99% availability. That is 4 nines.
To put that in perspective, 4 nines of availability equates to an allowance of barely 52 minutes of downtime for the entire year.
That's wild, but if your business is mission critical, say you are processing credit card authorizations globally, you can step up to a multi-regional setup. And this architecture is fascinating. The slides explain that your data is replicated across 4 zones in 2 entirely separate geographic regions, PLUS, a witness replica sitting in a 3rd region.
Witness replica acts as a tiebreaker.
A tiebreaker.
Yeah. If the network link between region A and region B gets severed, both regions might think the other one died. The witness replica in region C observes the landscape and casts the deciding vote on which region should take over as the primary, preventing a split-brain scenario where both regions try to write conflicting data.
By utilizing this multi-region architecture, your SLA jumps to 99.999%. 5 nines.
That translates to roughly 5 minutes of allowed downtime per year. The database is practically indestructible. Furthermore, slide 17 highlights that the RPO, the recovery point objective, is 0.
Recovery point objective refers to how much data you are willing to lose in a disaster. An RPO of 0 means that if a catastrophic earthquake completely levels a data center in Iowa, you lose exactly 0 bytes of data. Every single committed transaction was already perfectly replicated elsewhere.
But that level of invincibility introduces a profound physical constraint. The slide explicitly warns, write operations are slower, need quorum across more distant replicas.
You can't cheat physics.
Exactly. This is the concept of synchronous replication. When your application sends a write command to Firestore in a multi-region setup, the database engine cannot immediately tell the application, success, I saved it. It has to write the data locally and then send a copy of that data over fiber optic cables to the secondary region hundreds of miles away.
Right, over physical glass.
Yes, and it must wait for that secondary region to acknowledge receipt. That back-and-forth communication takes time, limited by the speed of light in glass.
So you are making a conscious architectural trade-off. You are accepting a slight increase in latency for every single write operation in exchange for absolute continent-spanning disaster survivability.
It is the eternal balancing act of distributed systems engineering.
Let's talk about day-to-day management, because managing billions of documents can get messy. Slide 20 introduces a feature called TTL, or time to live. You can set a policy based on a timestamp field inside a document, like an expire-at date. The slide says the system typically deletes the data within 72 hours after that timestamp passes.
This is a vital tool for cost management and legal compliance. Imagine you are building a system that stores user session tokens or temporary location tracking data for a delivery app. Privacy regulations might dictate that you cannot retain that data for more than 30 days.
So you'd have to write scripts to clean it up.
Exactly. Without TTL, you would have to dedicate engineering time to write custom batch scripts that wake up every night, scan the database, and delete old records. It's tedious and error-prone. With TTL, the database acts like a self-cleaning oven. You set the policy, and Google's background processes scrub the expired data automatically.
But I caught a very specific caveat on the slide. It says that deleting a document through a TTL policy does not automatically delete any sub-collections nested under that document.
That is a classic gotcha that results in bloated cloud bills.
Oh, I bet.
In Firestore, you can nest collections inside documents. Imagine a document representing a chat room, and nested inside it is a sub-collection containing thousands of messages. If your TTL policy expires the chat room document, the room itself vanishes. But the messages sub-collection remains intact, floating as orphan data in the database, totally disconnected from a parent, and you are still paying to store every byte of it.
Wow. So you're just paying for ghost data.
Yes. Your application's data model must account for cascading deletes if you use sub-collections.
That is exactly the kind of nuance an architect needs to know. Moving on to diagnostics, slide 21 shows a screenshot of a tool called Key Visualizer. It looks like a neon digital heat map. There are bright yellows, oranges, and dark purples. What exactly is this visualizing?
It is visualizing the most dangerous performance killer in a distributed database, hotspotting.
Hotspotting?
Yes. Firestore works its magic by automatically splitting your massive database across many different physical servers behind the scenes. But that load balancing relies on the assumption that your reads and writes are relatively evenly distributed across your data.
What happens if they aren't?
Imagine you build a mobile application for a massive reality TV show, and you have a document in Firestore that tracks the votes for a specific contestant. At the end of the show, the host says, "Vote now." And 5 million people simultaneously hit a button on their phone that tries to update that exact same document.
All 5 million requests get funneled to this single physical server that happens to hold that specific document.
And that server immediately melts down under the localized pressure. Latency spikes massively. The Key Visualizer provides a visual map of your access patterns over time. The dark purple areas represent normal distributed traffic. But if you see a blinding, solid vertical pillar of white or bright yellow on the graph, you are looking at a severe hotspot.
So it shows you exactly where the pain is.
It visually proves that your application architecture is funneling too much traffic to a narrow range of keys, and you need to radically redesign your data model, perhaps by distributing the vote counts across hundreds of shard documents to spread the thermal load.
It makes the invisible bottlenecks visible.
Okay, to wrap up our massive section on Firestore, the source materials do something excellent. They provide diagnostic question discussions, real-world scenarios that force you to apply all this theory.
Right.
I want to walk through a couple of these organically, dissecting the architectural problem.
Okay, let's do it. Look at the scenario presented on slides 25 and 26. We are tasked with designing a portal application for physicians. Crucially, it says this application will be used in hospitals and rural clinics that suffer from intermittent, unreliable internet connectivity. A core requirement is that if the internet drops, the application must still be able to query cached data. We also need scalability and multi-region replication.
This is a classic real-world constraint. Hospitals are notorious for terrible Wi-Fi due to the thick walls and medical equipment interference.
The slides provide a few potential solutions involving various Google Cloud databases, including Cloud Spanner and Memorystore. But the definitively correct architecture points directly back to what we discussed earlier regarding Firestore's native mode.
The defining clue in the prompt is the need for the client application to query cache data during a connectivity failure. While Cloud Spanner is an incredible, globally consistent database, it does not possess built-in client-side offline caching for mobile apps.
And Memorystore.
Memorystore is an in-memory cache, but it sits on the server side. It is completely useless to a mobile device that has lost its connection to the server.
But Firestore native mode, accessed via its mobile client libraries, has a feature specifically designed for this. You literally set a Boolean flag in the code called persistence enabled to true.
When you enable that, the Firestore SDK automatically creates a local miniaturized version of the database on the phone's physical storage. When the doctor enters an elevator and loses Wi-Fi, the app seamlessly switches to querying the local cache.
So they can keep working.
Exactly. The doctor can even write new medical notes, which are saved locally. When the phone reconnects to the network, the SDK quietly synchronizes those pending writes with the multi-region cloud database. It solves every constraint of the prompt natively without requiring the developer to build a custom syncing engine.
Let's dissect one more scenario from slides 27 and 28. This one is about optimizing delivery. The prompt describes an organization running a global news application backed by Firestore. The key detail is that it serves the exact same top 10 news stories on a daily basis to a massive global audience. The architectural goal is to decrease costs and decrease latency.
We have to analyze the current failure of the architecture. If millions of users in Tokyo, London, and Johannesburg open the app every morning, their phones are sending millions of individual read requests across the globe to the Firestore database, which might be sitting in a data center in Iowa.
And because Firestore charges you based on the number of document reads, querying the exact same static news story 5 million times incurs a massive unnecessary cost. Plus, the user in Tokyo suffers from the physical latency of the data traveling from Iowa.
Exactly. The database is working too hard to answer a question that never changes. One of the proposed solutions is deploying a multi-region Firestore location. But while that improves availability, it doesn't necessarily solve the latency for everyone globally, and it certainly doesn't reduce the billing cost of the millions of read operations.
The elegant solution highlighted by the slides involves something called a Firestore bundle combined with Cloud CDN. Walk us through how that intercepts the problem.
Cloud CDN stands for Content Delivery Network. It is a vast network of edge servers deployed in hundreds of cities around the world, physically close to the end users. A Firestore bundle is an advanced feature that allows a developer to package up the results of a specific query, in this case, the top 10 news documents, into a static serialized file.
You essentially take a snapshot of the dynamic data and freeze it into a static asset.
Yes. You generate this bundle once, and you deploy it to the Cloud CDN edge servers. Now, when our user in Tokyo opens the news app, their request never crosses the Pacific Ocean. It hits the CDN server sitting in Tokyo, the app downloads the bundle, and the local Firestore SDK unpacks it and serves it to the user.
So the latency is gone.
The latency drops to virtually zero. And crucially, because the application never actually queried the central Firestore database in Iowa, you pay zero document read costs. You have offloaded the read pressure to a highly efficient caching layer.
It's a beautiful architectural maneuver, and that provides the perfect logical transition. We just touched on the concept of caching to bypass the latency of physical distance. But sometimes you are dealing with applications where you don't just need fast delivery, you need computational speeds that are sub-millisecond.
We are shifting paradigms entirely.
We are moving away from storing data on magnetic disks or solid-state drives. We're moving into the volatile, blistering, fast realm of random access memory. Let's explore Cloud Memorystore.
This requires a totally different mindset regarding data permanence and architectural risk.
Slide 29 introduces Cloud Memorystore as a fully managed service for Redis and Memcached. It is explicitly categorized as an in-memory database. Let's look at the performance numbers, because slide 31 illustrates a scenario that is frankly wild. It maps out a typical web architecture attempting to handle 500,000 concurrent user sessions. Hitting a standard disk-based database, the architecture suffers from 200 milliseconds of latency.
Now, in human conversational terms, 200 milliseconds is a fifth of a second. Sounds fast. But in high-scale computing, when thousands of requests are queuing up every microsecond, 200 milliseconds is an eternity. It is a massive traffic jam that causes compute resources to back up, eventually crashing the web servers.
But the slide shows that by introducing Memorystore as a high-speed caching layer sitting between the web application and the main database, that latency drops from 200 milliseconds down to 50 milliseconds.
That is a 75% reduction in latency. And the implications are profound. It's not just that the end user perceives the web page loading slightly faster. By intercepting those 500,000 concurrent requests and answering them directly from memory, you are shielding your primary disk-based database from an immense amount of strain.
You're protecting it.
You are allowing your architecture to scale to levels that would destroy a traditional database, while simultaneously reducing your overall compute costs because you aren't paying your primary database to work as hard.
Slide 30 outlines the specific use cases where this microsecond latency is mandatory. Caching web content is obvious, but it also highlights gaming leaderboards, session stores, and fast data ingestion.
Think about the mechanics of a multiplayer gaming leaderboard. If you have 10 million people playing a battle royale game concurrently, the global leaderboard is recalculating and updating thousands of times every single second. You absolutely cannot write every single one of those fractional score changes to a persistent disk-based SQL database in real time.
It would just crash.
The disk I/O, the input-output operations, would hit a wall and the game would stutter. Instead, you keep the live, active leaderboard entirely within Memorystore's RAM, where it can be updated in microseconds. Then, a background process periodically takes a snapshot of that RAM and saves it to a persistent database for long-term historical storage.
Okay, this is where the architecture gets incredibly interesting, but also, frankly, terrifying. It is an in-memory database. It lives entirely in the RAM. Anyone who has ever used a computer knows that if the power cord is pulled, whatever is in the RAM evaporates instantly. It goes blank. How can any enterprise architect sleep at night knowing their data is sitting in a medium that wipes itself clean if the server reboots?
That volatility is the defining anxiety of in-memory architecture, and slides 33 and 34 address this anxiety directly by explaining how Google mitigates it through two distinct service tiers, the basic tier and the standard tier.
Let's examine the basic tier first.
The basic tier is exactly what you fear. It's a single, isolated Redis instance running on a single node. It is highly optimized for simple, ephemeral caching use cases. Crucially, if the underlying physical server experiences a hardware failure, or if you attempt to scale the instance up, or if Google performs routine maintenance, the instance restarts and the memory is flushed.
The data is just gone.
Gone completely. Furthermore, Google provides absolutely zero service level agreement for the basic tier.
Zero SLA. That means if the instance goes down for an hour, they don't owe you a dime in credits. It is purely best effort.
Exactly. You only ever utilize the basic tier for data that you can easily, cheaply, and quickly rebuild from your primary database if the cache gets wiped. It is cheap and fast, but it is architecturally fragile. Now, if your application demands reliability, you must utilize the standard tier.
The standard tier promises a 99.9% availability SLA. How does it achieve high availability if the underlying storage medium is still volatile RAM?
It achieves it through redundancy and automatic failover. When you provision a standard tier instance, Google secretly provisions two completely separate Redis instances behind the scenes. One acts as the primary node, absorbing all the active read and write traffic from your application. The other is a replica node, which is deliberately deployed in an entirely different availability zone to protect against a localized data center failure.
So if a backhoe cuts the power lines to Zone A, the primary node dies instantly, taking its RAM with it. But the system detects the heartbeat failure and automatically promotes the replica node sitting in Zone B to become the new primary node, taking over the traffic.
That is the mechanism. However, and this is a massive critical however, that every cloud architect must internalize, detailed explicitly in red text on slide 36.
Let's look at the specific phrasing regarding standard tier behavior. It states, replication is async using Redis asynchronous replication protocol. And immediately below that is the terrifying warning, ACK writes may be lost during failover.
This is the defining trade-off of the technology. We discussed synchronous replication earlier when we talked about Firestore's multi-region setup, where the database refuses to confirm a write until the data has safely traversed the network to a secondary location.
Right. Which guarantees safety but adds latency.
Precisely. Memorystore's entire reason for existence is to be as fast as physically possible. If it utilized synchronous replication, it would throttle the blistering RAM speed writes down to the speed of the cross-zone network link. It would defeat the entire purpose of an in-memory cache. Therefore, it is forced to use asynchronous replication.
Let's trace the exact sequence of events so we understand the danger.
Okay. Your application sends a piece of data to the primary node. The millisecond the data lands in the primary node's RAM, the node sends a message back to the application saying, "Success, I've got it. This is an acknowledged write." After it acknowledges the write to the app, a background process attempts to shoot a copy of that data over the network to the replica node in the other zone.
I see the vulnerability. What happens if the power fails on the primary node in that microscopic window of time after it told the app it had the data, but before it managed to send the background copy to the replica?
That specific piece of data evaporates into the ether. It is gone forever. The replica node in Zone B gets promoted to become the new primary, but it never received that final unsynchronized write. The slide explicitly warns developers app needs to be able to tolerate losing ACK writes.
Wow.
If losing a single microsecond level transaction will fundamentally corrupt your business logic, like a financial ledger, you absolutely cannot use an asynchronous in-memory cache as your primary source of truth.
It is a profound architectural reality. You are sacrificing absolute transactional safety at the microsecond level in exchange for raw, unadulterated speed. The slide also notes the physical impact on the application during the moment of failover. It says, existing connections are dropped and client needs to retry.
When the primary node in Zone A dies, the physical IP address your application was communicating with goes dead. Google's internal systems frantically update the DNS to point your connection string to the new primary node in Zone B, but that rerouting takes a few seconds. Any application queries that are in flight during that brief window will crash into a wall and receive a connection timeout error.
So the app just breaks for a second.
The application's source code must be engineered with resilience in mind. It must catch that error, pause for a moment, and attempt the connection again. You can never assume a persistent, unbreakable network connection in the cloud.
Moving beyond the anxiety of failovers, slide 40 details a powerful mechanism for scaling performance called read replicas.
This is essential for applications that are incredibly read-heavy. In the standard tier, you have the ability to provision up to 5 read replicas.
Consider a popular news website. They might write a new article once an hour, but they have 100,000 users reading articles every minute. The ratio of reads to writes is massive. You can spread that massive read load across up to 5 different Redis servers to ensure the latency stays at sub-millisecond levels.
Yes, and the architectural brilliance lies in how Google manages the traffic routing. The slide highlights that Memorystore provides a single read endpoint. If you manage this yourself on raw virtual machines, you would have to program your application's logic to constantly check the health of 5 different IP addresses and load balance requests between them, round-robin style.
That sounds exhausting.
With Memorystore, you point your application at one single IP address, and Google's internal invisible load balancers distribute the traffic perfectly across the replica nodes behind the scenes.
Let's discuss maintenance. Even fully managed serverless products run on physical Linux servers somewhere that require operating system patches. Slides 38 and 39 outline the maintenance policy. It states that maintenance occurs approximately once per quarter.
You cannot escape maintenance, but you are given control over the scheduling. You can configure a preferred maintenance window, for example, Sunday morning at 3 a.m.
The slide provides a highly specific operational recommendation. It advises setting the maintenance window when instance traffic is low or the system memory usage ratio metric is at 50% or lower. That 50% threshold seems arbitrary. Why is it dangerous to run maintenance if the memory is at 80% capacity?
This dives deep into the internal mechanics of how the Redis engine handles memory management during operations like background saves or synchronizing data with a new replica after a failover. Redis utilizes a process called forking.
Forking, okay.
When it needs to take a snapshot of the memory, it forks a child process. Because of how operating systems handle memory allocation during a fork, a concept called copy on write, the Redis instance might temporarily require almost double the amount of memory it is currently using to safely complete the snapshot.
Oh, so if your instance is hovering at 80% capacity and a maintenance event triggers a process that suddenly demands an extra 80%, you hit 160% memory utilization.
The server literally runs out of physical RAM. The operating system panics, triggers an out-of-memory killer, and the entire Redis instance crashes violently. Maintaining that 50% headroom is a critical safety margin to allow background processes to expand and contract without causing a catastrophic failure.
Let's examine how data moves in and out of the system because slides 41 and 42 cover the import and export processes, and they reveal behaviors that are radically different from a traditional database. The slide notes that import utilizes the native RDB snapshot feature of open source Redis, but there is a massive warning. Instance is unavailable during import and existing data gets overwritten.
An import operation in Memorystore is not a delicate, surgical insertion of new rows into an existing table. It is a blunt instrument. It is a wholesale replacement of reality.
A replacement of reality.
When you command Memorystore to import an RDB file from a cloud storage bucket, the instance immediately stops serving all application traffic. It then flushes its current memory completely clean and begins loading the new file into the empty RAM.
And then there's the most dramatic bullet point of all. Import cancellations result in full cache flush.
That specific behavior catches countless junior engineers off guard.
To be clear, if I start an import process, realize it's taking too long, and hit a cancel button, the system doesn't just gracefully roll back to the data it had 5 minutes ago, it completely flushes the cache and leaves me with a blank database.
Yes, because the very first step of the import process is to flush the existing memory, to make room for the incoming snapshot. If you abort the process halfway through, the old data is already permanently gone, and the new data is incomplete and corrupted. The only safe, stable state the engine can return to is empty.
Which explains why managing automated backups is so convoluted. Slide 42 outlines a process for scheduling exports. Memorystore does not have a simple checkbox in the console that says automate daily backups like Cloud SQL does.
It lacks that native feature, forcing architects to build their own automated workarounds.
The slide details an architecture that looks like a serverless Rube Goldberg machine. Let's trace it. Step 1, you configure a cloud scheduler job, basically a cloud-based cron job, to trigger at a specific time. Step 2, that scheduler posts a JSON message to a pub subtopic containing the Memorystore instance ID and the destination cloud storage bucket URL.
Right, passing the parameter.
Step 3, that pub sub message triggers a cloud function to execute. Step 4, the code running inside that cloud function authenticates itself and makes an API call to the Memorystore control plane, commanding it to execute an export and save the resulting RDB file to the storage bucket.
It is a complex chain of events, but it is a beautiful demonstration of how cloud-native building blocks work. You are using a serverless scheduler, an event-driven messaging queue, and a serverless compute function to patch a capability gap in a managed service.
Before we leave Memorystore, we have to tackle security. Slide 44 introduces VPC service controls.
This is a sophisticated, enterprise-grade security concept that is frequently misunderstood.
The slide states, VPC service controls protect against data exfiltration and provide an extra layer of security. But underneath that is a bolded limitation that seems to contradict it. It says, service perimeters protect only the Memorystore for Redis API. Perimeters do not protect normal data access on Memorystore for Redis instances within the same network.
This requires distinguishing between the control plane and the data plane. VPC service controls act as an invisible, high-level force field around the control plane, the APIs that manage the infrastructure itself. It is designed to prevent a specific nightmare scenario,
Which is
a rogue database administrator logs into the Google Cloud Console or uses the command line interface and executes a command to export the entire corporate Redis database to a personal, unauthenticated cloud storage bucket sitting outside the company's network. That is, API-driven exfiltration, and VPC service controls block it completely.
But the limitation means this force field does absolutely nothing to stop a compromised web server that is already sitting inside your network from simply connecting to the standard Redis port, running a JD command, and reading all the data directly out of the RAM.
Correct. The data plane, the actual querying of the data within the network, is entirely separate. VPC service controls do not intercept normal database queries. To protect the data plane, you still have to rely on traditional network firewalls, strict IAM, or identity and access management, roles, and robust in-transit encryption.
Speaking of encryption, slide 45 covers in-transit encryption. It notes that Memorystore supports encrypting all Redis traffic using TLS, or transport layer security. But it is not a simple toggle switch. The slide warns that you need a Redis client library that explicitly supports TLS A&D. You must have a certificate authority installed on the client machine.
You cannot just enforce encryption on the server side and assume everything will magically work. Cryptography requires a handshake. Both the client application and the server must participate. If you mandate TLS on your Memorystore instance, any application server that has not been meticulously configured with the correct certificate authority files will simply be rejected when it tries to connect. It requires coordinated configuration across your entire infrastructure.
Let's put all of this Memorystore theory to the test with two more architectural scenarios from the source materials. Let's analyze the problem presented on slides 48 and 49.
All right, what's the scenario?
We have an organization that needs to migrate an existing Redis database from their own physical on-premises data center up into a cloud-based Memorystore for Redis instance. The prompt specifically asks us to follow Google recommended practices to perform this migration, utilizing minimal cost, minimal time, and minimal effort.
We have to evaluate the proposed architectural pathways based on those three constraints: cost, time, and effort.
Let's dissect the options logically rather than just reading a list. We could try to set up a secondary instance on a virtual machine in the cloud and attempt a complex live replication cutover across the internet. Or we could write custom code, perhaps a data flow job or a complex shell script, to read the data from the on-premise server and write it item by item into the cloud instance. But the definitively correct architecture, according to the slide, leans on the blunt instrument we discussed earlier.
The optimal solution is to execute a native RDB export on the on-premises Redis server, securely transfer that resulting RDB file to a Google Cloud storage bucket, and then utilize the native Memorystore import function to load that file into the new instance.
Why is that better than writing a custom data pipeline script?
Because of the requirement for minimal effort. Building, testing, and monitoring a custom ETL pipeline, extract, transform, load, using Dataflow to migrate a simple Redis cache is massive over-engineering. It introduces unnecessary complexity and potential for code-level bugs. A live cutover across an unpredictable internet boundary is highly risky. Relying on the native RDB file format, which is the universal language of Redis, is the simplest, most robust, and most cost-effective pathway.
Let's tackle the final scenario from slides 50 and 51. This is a brilliant architectural brain teaser.
I love these.
The prompt states, you need to redesign the architecture of an application that currently uses Cloud SQL for PostgreSQL. The users of the application complain about slow query response times. You want to enhance your application architecture to offer sub-millisecond query latency.
We need to analyze the clues hidden within the problem statement. The foundation is Cloud SQL for PostgreSQL, which tells us the application fundamentally relies on a structured relational database. The core problem is slow query response times. But the most critical constraint, the phrase that dictates the entire solution, is the demand for sub-millisecond query latency.
Sub-millisecond. Not just fast, but nearly instantaneous.
Exactly. One instinct might be to add read replicas to the existing PostgreSQL database. While that would increase the overall throughput capacity and handle more concurrent users, a traditional disk-based relational database will always struggle to consistently deliver guaranteed sub-millisecond latency for complex queries due to the physical limitations of disk I/O.
Another instinct might be to completely rip out the relational database and rewrite the application to use a blazing fast NoSQL engine like Bigtable or Firestore.
But that violates the principle of operational sanity. Migrating an application from a relational SQL paradigm to a NoSQL paradigm is a catastrophic undertaking. It requires rewriting the entire data access layer, retraining the developers, and abandoning the AC transaction guarantees the application might rely on. It is building a completely different custom sports car when you just need to go a little faster.
The elegant solution, the one that solves the problem without destroying the existing foundation, is introducing Memorystore.
You preserve your reliable, structured PostgreSQL database as the ultimate single source of truth. It remains the system of record. But you introduce Memorystore as an in-memory caching layer directly in front of it. You subtly modify the application's logic to implement a read-through cache pattern.
Read-through.
When a user requests data, the application checks Memorystore first. If the data is present in RAM, it returns it to the user in microseconds, achieving the sub-millisecond goal. If the data is absent, a cache miss, the application queries PostgreSQL, returns the data to the user, and simultaneously writes a copy of that data into Memorystore so the next user experiences microsecond latency. You achieve incredible speed while maintaining relational integrity.
It is the perfect architectural synergy. You let disks do what disks are good at, permanent storage, and you let RAM do what RAM is good at, blistering speed. All right, we are entering the final segment of our deep dive.
The home stretch.
We have built robust transactional applications running on Kubernetes. We have designed wildly flexible, horizontally scaling global user profiles using Firestore. We have strapped microsecond latency caching layers to our architectures using Memorystore. We have data scattered everywhere. It exists across multiple regions, across SQL and NoSQL formats, sitting on magnetic disks and evaporating in volatile memory. In a massive enterprise environment, how on earth does a company keep track of this chaotic landscape without descending into total operational anarchy?
That is the central existential crisis of modern data engineering. You can provision the most powerful, elegantly designed databases in the world, but if your company's data scientists, analysts, and security auditors do not know where the data physically resides or what the columns actually mean, the data is functionally useless.
It's just noise.
It is a liability rather than an asset. This is precisely the problem Data Catalog is engineered to solve, which is detailed starting on slide 52.
Slide 53 introduces the core philosophy, the why of Data Catalog. And the very first bullet point describes it with a brilliant comparison. It states that Data Catalog simplifies data discovery for customers at any scale. Quickly and easily find data assets with Google search technology that supports Gmail and Drive.
Think deeply about how you interact with your personal Google Drive. You likely have thousands of files collected over a decade. You don't memorize the exact nested folder structure you buried a specific PDF in 3 years ago.
No, you just search for it.
You simply type a keyword into the search bar, and the underlying algorithm instantly scans millions of files, parses the text within them, and surfaces the correct document. Data Catalog takes that exact same algorithmic search power and applies it to your corporation's entire internal data ecosystem. It scans your Cloud SQL databases, your BigQuery data warehouses, your pub/sub messaging streams, and indexes them all into a single searchable interface.
It transforms tribal knowledge, where you have to ask a senior engineer which database holds the customer emails, into algorithmic discovery.
Yes. The second crucial point on the slide is that it provides a unified view by capturing two distinct types of metadata: technical metadata and business metadata.
This distinction is vital for understanding data governance. Let's break down the difference with concrete examples. What constitutes technical metadata versus business metadata?
Technical metadata is the hard, inflexible reality of the infrastructure. It's the database schema itself. What is the physical name of this table? What is the name of this specific column? Is the data type a string, an integer, or a Boolean? On what exact timestamp was this table created, and how many bytes of storage does it consume? This information is harvested automatically by Data Catalog crawling the infrastructure.
And the business side?
Business metadata provides the human context. Who is the executive owner of this dataset? What specific business department generated it? Is the information contained in this column considered highly confidential under GDPR? Is this string of characters an email address, a social security number, or just a random product ID? This context cannot be inferred purely from the database schema. It must be mapped and applied by human data stewards or automated classification engines.
The analogy that solidifies this for me is a massive municipal library. An uncatalogued library is just a warehouse full of paper. It is chaos. Data Catalog acts as a hyper-organized, nearly omniscient librarian. The librarian knows the exact physical location of every single book on every shelf. That is the technical metadata. But the librarian also knows exactly which pages of a specific book contain sensitive information, who checked the book out last week, and what the strict corporate policy is regarding who is allowed to read it. That is the business metadata.
It is a flawless analogy, and that business context leads directly into the third capability highlighted on the slide, providing a foundation for robust data governance. Slide 54 features a screenshot illustrating tags and data governance. It displays an interface where administrators can attach tag templates to specific granular elements within a database down to the individual column level.
Looking at the screenshot, they are examining a specific database column, and the tag template attached to it has fields like is encrypted, featuring a simple true-false dropdown. It also has a tag for hash PII, indicating personally identifiable information, and then a specific PII type tag, which in this instance is set to email.
This is the exact point where Data Catalog evolves from a simple search engine into a terrifyingly powerful security and compliance enforcement mechanism. You are not merely attaching digital sticky notes to data for organizational sake. By explicitly tagging a column as containing PII, you are plugging that data asset directly into the broader Google Cloud security ecosystem.
The slide explicitly calls out strong security and compliance with DLP API and Cloud IAM integration.
DLP is the Data Loss Prevention API. a machine learning tool that can scan data to automatically identify credit card numbers or social security numbers and apply those tags automatically. But the true power lies in the integration with IAM, identity, and access management. Because Data Catalog feeds these tags into the central security nervous system, you can write dynamic security policies based on the metadata rather than the physical database structure.
Explain how that works in practice.
Imagine you have a massive user database. A junior developer might be granted legitimate IAM permissions to query that database to troubleshoot a bug. But using Data Catalog, the security team has written a policy stating, only users explicitly assigned to the Human Resources IAM group have permission to view any column globally tagged with PII-type email. Even though the junior developer has raw read access to the database tables, when they run a query, the governance layer intercepts it, consults the data catalog tags, and dynamically masks or completely restricts access to the specific column containing the emails.
It applies fine-grained, policy-driven control over a massive, chaotic landscape. It doesn't matter if the developer moves that data to a new table. If the tag follows the data, the security policy follows the data. It brings absolute order to the muddy waters of cloud architecture.
Exactly.
Well, we have covered an immense expanse of architectural theory today. We began by examining the bedrock foundation, establishing the golden rule that architects should default to fully managed services to save themselves from the grueling toil of operations, unless their business demands the agonizing custom-built control of running stateful databases on Kubernetes.
We've entered into the wildly flexible, horizontally scaling universe of NoSQL with Firestore, untangling the confusing name game and dissecting the mathematical necessity of strict indexing rules to guarantee performance at a global scale.
We then subjected ourselves to the terrifying volatility of random access memory, strapping the microsecond speeds of Memorystore caching to our applications while navigating the inherent dangers of asynchronous failover replication and the complexities of automated exports. And finally, we brought order to the chaos by governing our multi-layered architectures with the search engine capabilities and policy-driven tagging of Data Catalog.
It provides a comprehensive 360-degree view of how modern, massive-scale systems breathe, scale, and protect themselves.
To close out this journey, I want to reflect on the nature of what we've learned. We have spent this entire deep dive meticulously categorizing technologies. We drew thick lines separating the rigid transactional structure of SQL from the flexible dynamic documents of NoSQL. We drew even thicker lines separating permanent slow disk storage with Firestore from the volatile, blistering speed of memory with Memorystore. We put every technology in its correct, neatly labeled architectural box. But as we look toward the horizon of infrastructure evolution, I want to pose a theoretical question.
The rigid boundaries you mentioned exist almost entirely due to the physical limitations of our current hardware generation. Magnetic disks and standard solid-state drives are relatively slow but incredibly cheap, while RAM is incredibly fast, but volatile and expensive. We construct these elaborate multi-layered architectures specifically to bypass those physical realities. But let's extrapolate into the future. Hardware is evolving rapidly. As persistent storage technologies like NVMe approach the speeds of traditional RAM, and as memory itself becomes vastly cheaper and non-volatile, retaining data even when power is lost, will there come a day when these two distinct concepts merge? Will the cloud database of the future be a single, unimaginably intelligent entity that autonomously decides, on a microsecond-by-microsecond basis, whether a specific byte of data belongs in memory or on disk, rendering the complex, multi-layered architectural decisions we agonize over today entirely obsolete?
That is a staggering thought to leave on. The intricate architecture we spend years learning to master might eventually just be automated away by the very systems we are building. The concrete foundation won't just become liquid, it will become intelligent and self-assembling. To you, the listener tuning in right now, keep questioning the rigid structures you see, keep exploring the hidden trade-offs beneath the marketing materials, and remember that in cloud architecture, there is always more beneath the surface. Thanks for joining us on this deep dive.